So, simulation, what can we do in SolidWorks and why it is important? So, first of all, why it has advantages, why should we use this? Well, first of all, when you want to create any product, anything that you want to market, sell, one of the most important part is analysis and simulation, because typically the first time you design something, it's not going to be the final cut, right? You probably in the first round of design, you're not going to be able to meet all the requirements. There are some shortcomings that you have to keep working on. That's why we call what we call a design cycle. And now the problem is, let's say, how do I know the design that I made is going to work? Well, some of you might say, well, I gotta make it. I gotta make a prototype and check it whether it's work or not. Fine, but if this design cycle is gonna take several rounds of iterations, that means you have to make the prototype several times, and that means time and cost. Not all prototypes are cheap and fast and easy to make. So one of the things you do is, instead of making the real life physical prototype, you just make a CAD model of that, and then in a computer simulation you try to mimic the behavior of the actual physical prototype under loads, under all sorts of conditions that it has to serve, and see whether it works or not. Now, does it mean that the simulation is exactly like the physical prototype? No, they are different. You most probably can never make anything in simulation that is 100% like real life, but at least it can give you intuitions. It can give you some feedback on which parts of this design has to be modified before you go for a prototype. So saving a lot of time and money is one of the major advantages. Sometimes, on the other hand, you cannot even make a fully working prototype and test it because, well, it could be really expensive. It could be impossible to experiment it in real life or so on, right? Let's say you want to design a dam, correct? You cannot make a dam and then go put it there and then let water be collected behind the dam and see what happens. Well, you have to first do a ton of basically simulation before you even start making the actual dam. And the fact is, you might say, well, I might make a mini dam. Yes, but in real life, many of the stuff are not just linearly proportional to their size. So for example, well, if I make the dam 10 times smaller or 100 times smaller, then that means all of the forces that will be applied to it will be also 100 times smaller. So not everything is just acting linear. Or let's say you are making a Mars rover, right? So where would you test it even if you make it? You cannot. You have to rely on your simulation before you make one, and then take a ton of money and effort to send it to the Mars. So for some stuff, you'd have no chance of testing the real life. You have to rely on your simulation heavily. So I told you that it gives you insight and make you optimize your designs. And sometimes also the input to your system is quite random. You cannot always exactly know what are the inputs, what are the loads, what are all sorts of things that will be applied to your system. Some of them have a random nature. And so in those situations, you have to do a simulation to get an average sense of what your system might do. One of those is like called Monte Carlo simulation. I don't know if you heard of it or not, but that's what they do in the casino and gambling businesses, that they try to find the outcome of so many random things. So that is really important and we have to do it. Now, what can we really do in SolidWorks? Well, one of the things we can do, the major one, is statics analysis. So this is analysis on parts that are not moving, structures, stationary stuff, and we apply loads on them, whether the load is a physical load like a force or torque, or is a thermal load, and we see the behavior of them, how they would deform, the stress that is created inside them, whether they would fail or not. The other is frequency or vibration analysis, so we look at the vibrations of the structures. The other one is buckling. Buckling is when you apply pressure on a column and see whether the column is bending laterally, right? Like when you have a can of soda and you put your foot on it and keep pushing down until it buckles. Then we have, of course, thermal. Thermal can be completely separate of its own or be included in the statics, combined with the statics. In new adds-in in SolidWorks, you can even do fluid vibrations and fluid analysis. You can do fatigue analysis, which means applying a load that is changing with time. The magnitude of the load is changing, and that will ruin the part, that will wear down the part much faster than expected because it makes micro cracks inside the part grow. Like, for example, if you have a small piece of metal that you cannot easily break, but what you do is you bend it forward and backward in different directions, right? And that will make the part break much faster. You can do design studies. That design cycle, you can analyze nonlinear systems, linear system dynamics, even drop test. These are really advanced stuff, topology studies, and pressure vessel designs. Now, typically, when you go down this list, these are the kind of designs that you get with a more advanced or more expensive SolidWorks license. So not all of these are available in a basic student's license, but as you go first to our premium and then to our commercial SolidWorks licenses, which are getting more and more expensive, then yes, you will probably see all of these. But what I want to focus today is statics, and if time allows, maybe just very briefly a vibration or frequency analysis. So let's talk about the static analysis. So let's first talk about something that you need to know, although again this thing you have to learn in solid mechanics, but if you want to understand this lecture, I have to briefly discuss it. So, and that's the notion of stress and strain. So what is stress? As I told you in a previous lecture, like us, when there is some mental pressure on us, correct? There are like homework due, exam due, quiz, this and that, and we don't have time and we develop a mental stress. The same thing happened to physical parts, but for them, what is causing the stress is external load like force or torque. So if you have like a rod that is fixed on one side and on the other side you're pulling it down, by the way, this is called a uniaxial experiment. It's a uniaxial tension experiment, okay, or tensile experiment. Then inside the part is created something called stress, and the bigger force P you apply, the bigger the stress becomes, and this stress can go up, up, up until some limit, some capacity of the material, which is called strength. So strength is a natural inherent property of the material, like steel has more strength than aluminum, for example. And stress, once below the strength, the part typically is okay. once the stress surpasses the strength, is getting bigger than the strength, that's where the part starts to deform and then ultimately fail and break. Right? So this is the basic of design. Never make a stress more than the capacity of the material. Never make it more than strength. Right? That's the basic. So now, how would you exactly mathematically define a stress? We define a stress to be the force divided by the area. So if force P is divided by an area where the section area is A, then P divided by A is called a stress. Clearly, the unit for that is Newton per meter squared, which is called Pascal, or pound force per inch squared, which is PSI. And this is called a normal stress. We show it with sigma, and the reason we call it normal stress is because this force P that you see is normal to that surface, is perpendicular to that surface, so we call it normal stress. And the effect of normal stress is clearly what? If I apply a normal force P like that to the rod, what do you expect to happen? Well, probably you expect that it changes the length of the rod. It makes the rod longer, right? Or if you press it inward, it makes it shorter. So the effect of that, the deformation, the effect of that, we measure by something called strain. What is a strain? Strain is the new length after you apply the force minus the original length divided by the original length, or you can also write it as delta L divided by L. And we show it, this normal strain, we show it by letter epsilon, and it does not have any unit because it's like meter divided by meter or inch divided by inch, so it's a unitless quantity. Now, as I said, this is called normal stress, normal strain, because your force is normal to the surface, right? It's perpendicular to the surface. Now, is there any other situation? Yes. So sometimes you have like a part like this again. There is a part like this, but the force P, instead of being, so let me show it in 3D. So instead of the force P being normal to the cross-section A, it is tangent like this to the cross-section P. In that case, if I divide P by that section A, so in this case, I can call this P normal, and I can call this P parallel. So if I divide P parallel by A, or P tangent by A, there is another type of stress which we call shear stress, and shear stress is shown by letter tau. Tau is similar to sigma, the unit is the same, Pascal or PSI, but the behavior is different, because if you apply this force to that part, what do you expect? It's not going to make the part longer or shorter. What it does, it deforms the object angles, right? I mean, like if you look at this from the side, what happens? So if this is the initial shape of the part, when you apply this force, P parallel, what happens? Yes, the angles would deform and it becomes something like this, like a parallelogram. So this much, the vertical angles, the 90-degree angles have changed. This gamma is the change in the right angles, okay? It is in radians, this gamma. It's the change in these vertical angles, and this gamma, which again has unit of radian, we call it what? We call it shear strain. So this guy is called normal strain, and this is normal stress. But this one is shear stress, and the effect of that change in the right angle is called shear strain. Okay, so these are shear and shear. Those are normal and normal. So these are the two types of stress and strain that we have. Now the question is, are these strain and stress related? Well, probably yes, right? Because of course, if you apply more force per area, more stress inside the part, you probably expect what? More elongation, right? More change in the length. So they should be related, but how? Is the relation linear? I mean, like if I make the force 2 times bigger, do I expect the elongation to be 2 times bigger, or 3 times, or 1.5? What is that? Well, I'll show you how it behaves. But one last thing I wanted to mention is the sigma, the normal stress. If this force P is outward, in other words, it is creating tension or tensile, then the sigma is considered positive. If force P is inward and pushing the part in, is creating a compression, then the compressive stress, we show it with what? With negative. So if it's tensile, we say positive, and if it's compressive, we call it negative. Okay? Now the question again was, how are these two related? And for that, we have to look at something called a tensile test. So let me show you this video. So this is a video of a tensile test where you have a specimen, a part that is fixed between the two jaws of this mechanism, and then you start applying a tensile force which make the part longer and longer, and then you attach this extensometer to the part which measures the elongation. So you can both measure the amount of force that is applied, the tensile force, on a computer, and then you can also measure the amount of elongation, and you can plot it over here, force versus elongation, or a stress versus strain. And you keep increasing the force until the part changes shape and finally breaks. Okay, so you see here is the part that the force is so high that makes this section of the part goes narrower, right? So you see the cross section of the part is narrower here. This thing we call necking. And ultimately at that point, that's where the part starts to break at 45-degree angle. So it's getting smaller and smaller, stress goes higher and higher, and there we go. We have failure. Okay, so now that we saw the video, as I said, you're gonna get the graph, and that graph would look something like this for structural steel. That graph would look differently for each different material, but this is the typical tensile test for structural steel. As you can see in the beginning, as the force is getting higher and higher, or the stress is increasing, I have a linear region. This linear region is where a stress and a strain are proportional to each other, right? They are linearly proportional. So stress 2 times bigger means elongation or strain 2 times bigger. Now the slope of this line, or the constant of the line, the slope of the line is a property of the material. So if I show sigma as a number times epsilon, the slope of that line, this constant E, which is the slope of this line, it is a property of the material which we call modulus of elasticity, or we call it Young modulus. And that's what you see here. This Young modulus has units of stress, so it is also in Pascal or PSI, and each material has its own numbers. So for example, if you look at steel, you see that the E, the slope for steel, is 30 million psi, while for aluminum is 10 million psi. Okay, so that's this E, which you can see for aluminum and steel, and these are ranges for other numbers like fiberglass and graphite. So the other thing important about this region is, let's say I increase the force and the current point of the experiment is here. So the force is That stress, of course, times the cross section, and then the elongation is this elongation. The elongation is this strain times the original length, right? So now the question is, what happens if I turn the machine off? If I turn the experiment machine off? So I gone from origin up to here, and now I switch the machine off. What do you think would happen? By turning off means what? Means the force should go back to 0. So the force goes back to 0, but does also the elongation, the strain, goes back to 0. In other words, if I go up to here when I turn the machine off, am I going to move back on the same line back to the origin? The answer is yes, I do. In other words, the material acts exactly like what? Like a linear spring, like an elastic or rubber band that you haven't pulled or pushed too much. It goes back to the original length. So that's why we call this region the elastic region or linear region. Okay, that's the same name, elastic region or linear region. But after this region ends, after your stress passed some limit, which we call it yield stress, and that's another very important property of any material, after that the material would act differently. First, in this BC region, without me increasing the force too much, you see I can get a lot of elongation. So the material here, what we call the material yields. So although I'm not increasing the force much, it's almost horizontal, but the material yields and elongate without me pushing further or pulling further. Then after that, the material starts to resist again, and this is the area I call strain hardening. So now if I want more elongation between C to D, I need more force. And the material reaches the maximum stress that it can tolerate. We call that the ultimate stress, or sigma sub u. This yield stress, we call it sigma sub y. And then it keeps going, and from D to E, that's that area that you saw the cross section of the material starts to basically shrink like this, right? So you probably saw this, that's the nicking. And finally it will fail here. So any part from area B or A to E, all this region from here to here, we call it the plastic region. Why we call it plastic region? Because at any point here, if I turn the machine off, let's say here, I'm here and I turn the machine off, what do you think would happen? Am I going to go back all the way on this curve back to the origin? The answer is no. I will go back to 0 force or 0 stress because, of course, the machine is turned off. But the elongation will not be 0. How do I go back? I go back on a line parallel to OA. So if I draw a line from this point parallel to OA like this, so this line is parallel to OA. I hit the horizontal axis here. So yes, at this point now, the force is 0, but I have this much of elongation that is not going to go away. And I call that what? I call it permanent elongation. That's an indication of permanent elongation. It is never going to go back to the original shape because the material has deformed permanently. So we call that region plastic. Now we as engineers, we always want to stick to this region. We never want, after the machine is under load and is working, but when we turn the machine off, we don't want the size of the machine change. One of the examples that I always say as kind of like a joke to my class is, you don't want to fly an airplane from here to Phoenix or somewhere else, and you fly a Cessna airplane, and then when you land in Phoenix, it's a Boeing 477 or something, right? You don't want the material to change, or you don't want to start working with a mini lathe machine or milling machine, and after the machine turned off, you see that it is now a mid-size range. So you always want to stick to the region where if you turn everything off, it goes back to the original length. So we always want to stick to this region, and so this number is extremely important to us. We never want the stress in material to pass this yield stress. We should always stay, the stress in material should always stay less than yield stress. That's how you design, okay? And you see that the yield stress, for example, for aluminum is 35,000 psi, and for mild steel is 60,000 psi. For graphite composite, it can go to 200,000. For fiberglass, it's between 20 to 35k psi. Okay, so it shows basically how far you can go with these material before they start to deform permanently. So now, when you want to design, as I said, you always make sure your stress is less than the yield stress. But not only that, we engineers are always cautious. What do? Not only we make sure that the stress, which is calculated by P over A, never passes or exceeds sigma y. Not only that, we make sure that it's always less than sigma y divided by a number, where that number is more than 1. For example, if that number is 2, what does it mean? It means my stress is never past half of sigma y. In other words, I'm just using 50% of the capacity of the material. The other 50% of the strength of the material, I keep it as a safety. Okay, I'm not going to use it. So this number in the denominator, this number which is more than 1, we call it a safety coefficient or safety factor. Okay, so this guy is called a safety factor. And why do we use that? What's the indication? So why do we use it? Because we are not always sure how much force in real life is actually applied to the part. One example I mentioned is the airplane, of course, right? Airplane, you design it for standard operations, everything, but all of a sudden you have a huge turbulence in the air. And you don't really know how big the turbulence is and how much force it will apply to the wings of your airplane. So if you design the wings of the airplane so thin that the only force you consider for them is the lift and the drag and no turbulence, then when a huge turbulence comes, then you might see your wings break. Or if you have an elevator, right? And you wrote on the elevator that the capacity of this elevator is 10 people only, but that elevator is so slow, like the one in AC1, that every once in a while it comes down. So when it does, there are a ton of people waiting and they don't want to wait again. So now instead of 10 people, you see 20 people are crammed into and squeezed into the elevator. So you design it for 10, but 20 people jump in. And what happens? Yes, you're going to see the rope fails and kills everybody. So because of uncertainty in the force or the load or thermal or all sorts of other loading that might happen to the object, and you're not sure about it ahead of time, you cannot model it, you always consider some safety factor. And the more uncertain you are, the bigger safety factor you would use. It's quite interesting that for elevators, you are using a safety factor of 10 to 12. In other words, the rope of the elevator is so thick that you are only using 8 to 10% of its strength for 10 people. Okay? Or 5 people or whatever people that you write on the door of the elevator. So, because you don't want to take chances. You want to be extremely conservative in the design of those. That's one reason. The other reason is, other than uncertainty in loading, it's this number here. So you bought some steel to make something, you bought a rope to make something for elevator, and the manufacturer says this number is 10,000 psi. Well, does it mean that whatever rope that you buy from that manufacturer, the yield strength for them is 10,000 psi? No. It's just an average that they are reporting out of all their different things that they are making. If you take probably 10 of them and test them like that tensile test that I showed you, then you probably see a range of numbers, right? You would see a range of numbers where it might have a normal distribution like this, and then here, so this is the number of the samples that you found having that value of sigma y, and this is sigma y, and then the average might be something like 10,000, while the lowest one could be like 9,000, and maybe the highest one be 11,000. So you never know exactly which one of those you will get out of a manufacturer. And this is all assuming that they are saying the truth. Now, many manufacturers, not many, but a bunch of them do not exactly tell you the truth. They exaggerate their numbers to sell better. So they say 10,000, but maybe even if you take a ton of samples out of them and test them, you see that no, really their average is 8, not 10. They are exaggerating it. So you cannot rely on an average in statistics, and you cannot rely on the word of a manufacturer, so this number is also not certain. And there are so many other uncertainties that will make you only use a portion of the total capacity, and you always use safety factor. Now, of course, when the safety factor goes up, in order to keep this inequality that P over A is less than sigma y over SF, you also need to make what? If you say P, the force is fixed, assuming that it is fixed, to keep this inequality and this material is also fixed. So you chosen your material, the loading is fixed, you just make safety factor bigger. What does it imply for the cross section? Yes, that guy has to go up to keep the inequality. And what does it mean? When cross-section goes up, it means you are using more material. You are having more hefty designs. And hefty designs means more time, more money, and bigger parts that are not easy to move and handle. So it's not really good many times to do what we call over-design. So if you use a safety factor which is way more than what it should be, we call it an over-design. You should not over-design, but you should not always you should never under-design too, and especially when the life of human being is involved. So how do I know how much of safety factor I should use? There are standards for each operation. When you want to design an elevator, there are ASME standards for designing elevators, for designing pressure vessels, for designing this and that. When you want to design an airplane, there is AIAA standards for designing those, and ASME is American Society of Mechanical Engineers. And they would tell you based on experience how much of safety factor is a good number. Okay, now that you have learned about basics, let's go back and talk about some other things. So let me get this out of here for a moment. Let's take it where it belongs, and then we'll talk about it later. But where's the stress? I'll put it here for a moment. So now, when we want to do something in SolidWorks, let's say we want to repeat this experiment together in SolidWorks. So we want to have a rod with length L cross-section A and choose it from a material that has a Young modulus of E, and we apply a load of P to it. Then the question is, how much is the stress inside this object, and how much it is going to elongate? How much how much the length of it is going to be longer after this tensile experiment? So if you take solid mechanics, you will learn that the normal stress in this part is sigma is going to be the force that you apply P over the cross section of the rod. Now in this case, what I want to experiment with you is I want to choose a rod with a diameter of 1 inch. So from that you can find the cross section. And I want to apply on one end of it a load P, which is 10,000 pounds. If I use that force and that cross section, theory would tell me that the stress inside the part should be 12,732 psi. Okay, that's how much stress I expect in the part. And then how much is the elongation? Well, I choose the initial length to be 20 inches, and I choose aluminum 1060 with this much of Young modulus, 1.015 times 10 to the 7 psi. And then again, in your solid mechanics, you'll find in this simple uniaxial tensile test, the amount of elongation changing the length, this delta is the same as that delta L I mentioned, is going to be PL over EA. It's not hard to show it. And if I plug PLEA from here, you see that after applying that 10,000 pound force on that aluminum rod, you should get 0.0251 inch of change in the length. So this is what you're going to learn in your course ES202, Solid Mechanics. This is theory. But now when I do it in SolidWorks, how does SolidWorks calculate this number? Does SolidWorks follow the same formulas like this one and this one? Or it does solve it in a different way? Well, not only SolidWorks, most other softwares, as far as I know, that tackle these problems of stress and statics problems, they use a numerical method for solution. They do not use exact formulas like this. Why? Because there are infinitely many designs and all sorts of different combination of loading and geometry, and these two simple formulas that you saw are only for this simple experiment, uniaxial tensile test. If now you apply the force instead of tensile, if you apply a tangent force, then the behavior will be different. You're going to see bending. And then if this part is now different and it's not a simple rod, it's like an L-shaped rod like this, and then you apply a force at angle which has both a bending effect and tension effect and then shear stress and so on. So you're going to learn that in ES202. It's called combined loading. Then that is going to be much more complicated. And you cannot keep giving your SolidWorks infinitely many formulas. It's not possible. So there is a numerical method for solving any kind of complicated loading, complicated geometry. And that numerical solution, if you apply it properly, will give you a number that is hopefully quite close to the actual theory. Okay? So it's quite accurate if you properly apply it, and I'll show you points about that. But what is this method called? The method is called FEA, or Finite Element Analysis. Sorry for my bad handwriting, but it is really hard to write on a slippery computer screen. So FEA, or Finite Element Analysis, is a numerical method where you break down the part into a lot of small elements, a finite number of small elements, or what we create a mesh, and then we apply the FEA method to solve for all of these numbers. Now, the detail about this method is way beyond the scope of this class. There is a course for FEA actually, which is like a 5,000 level course. It's a graduate level course, and we don't really offer such a thing here. Some of you might see it in a machine design course for AE students, maybe in their aerostructure, briefly, not as a formal topic. And they might use another software for doing this FEA instead of SolidWorks. The most famous software that does this FEA method for all sorts of conditions, you probably heard of it. The software is called ANSYS. And that can handle much more complicated problems than a simple SolidWorks. But for the sake of this course and demo, I guess this is enough. Now, when we want to do an FEA problem, for now, it is like a magic box. I cannot at the moment explain to you how it is exactly solving it, but when you pass a problem to a FEA solver, you need to make sure you have prepared it properly. What do I mean? In addition to the geometry of the part, which in this case is simple, just a cylinder, you need some other things fixed and defined before you start the simulation. One is material. So not only you have to have geometry, you also have to apply material. Then the connections and fixtures. So in this case, what do I have? I have this part, this end, which is fixed to the wall. It's called a cantilevered or fixed connection. So I have to define that. Then any external load that is applied to the part, including force, torque, pressure. Of course, pressure is a form of stress. We learned, right? It's a negative normal stress. If there is gravity, if there is bearing load, temperature, centrifugal, and so on. In this case, again, it is quite simple. It's just this external load P. And finally, the mesh, or this finite number of small elements. So we need to apply all of that, right? So let's first do it. I'll show you how to do that, and then we'll continue. So we have to keep in mind, this is what we want. Aluminum, that length, that diameter. So let's get to it. So here I load SolidWorks and I create a shaft on the front plane. Make sure the units are IPS. They are right now. Diameter 1 inch. Extruded for 20. Then apply material to it, aluminum 1060. Now it is ready. So what we do is, now we click on the simulation tab. Okay, if you don't see it, you go under Tools, Add-ins, and make sure that this one here, SolidWorks Simulation, is checked and active. If it's not, check it. So now you click on the Simulation tab and then you click on New Study. Then it says, what do you want? And you say, I want a static test, because this part is not supposed to move. It is fixed on one end to the wall. And you okay that. And now here you see the part has a tree for itself where you have to define connections or fixtures, load, mesh it, and so on and so forth. And all of those items are also seen here on the top. So first thing is you want a fixture, right? So if you go to this connection advisor, right? And you see I have some stuff like spring, pin, bolt, bearing, and so on, but these are some kind of things that you might need, not in this case. The other one is here under fixture advisor, And the one that you need in this case is this guy here called fixed geometry. But there is roller, fixed hinge, elastic support, and so on if you want to apply. But again, as I said, I want fixed geometry, so I click on it, and then you apply it to this surface, and you OK that. So now that part here is gonna be completely stationary. Then you go to the other side, and this is the part for external load, where you can apply force, torque, pressure, gravity, bearing load, temperature, thermofluid, so many things, right? And I go for force, and then I click on this face. As you can see right now, the force is inward, normal but inward, so which make compression, not tension. So one of the things I need to do is, first I check this guy says reverse direction, so now it's tension, and then the unit I change it from SI to the English system, and the pound force, if you remember, it was 10,000 pound force, right? So that's the amount of force that I need, and I OK that. So now the force is applied, the material, geometry, everything is in this slide is applied except for mesh. And now we are going to convert this into a lot of small elements, and then we solve the problem. By the way, what's the shape of these elements? So let me first mesh it, but the shape of them is this guy here, which is called a tetrahedron. And tetrahedron is basically a shape with 4 faces. The basic one is 4 faces, all of them are triangles, right? So you have a triangle at the base, and then 3 triangles on the 3 other sides. So this is the simplest basic shape that you can use. There are other shapes too. Now the basic one has only 4 nodes. Nodes are the connection points, the calculation points, the points that the displacement of which should be calculated in XYZ direction. This is the simplest. You can have more advanced ones where it's still like a tetrahedron, but it has a bunch of extra nodes on it. On each edge you also see 1 extra node. So instead of 4 faces, 4 nodes, this has 4 faces but 10 nodes. And it has more calculation, which means finer results. Okay, more accurate results, of course, at the expense of more computation time. So now we have to do mesh. Now, let me tell you something about mesh. If your object is bulky and rigid, use rigid mesh, and I'll show you. SolidWorks has several types of meshes. If it's bulky rigid, you use rigid mesh. If there are thin parts like sheet metals, right? In this course we learn how to do sheet metals. For sheet metals, do not use rigid mesh. There is another mesh in it. It's called basically a shell mesh. That is basically the type of mesh that you use for thin objects. And if the objects are very long with constant cross-section, you can use a beam mesh. In this example, I can also use a beam mesh too, because it's quite long with a constant cross-section. So I can use beam mesh, rigid mesh, or shell mesh in SolidWorks. In this example, I either have to use rigid or beam, and I go with rigid, which is the simplest one. So if you go here, now you have to, so you see clearly that the fixture is defined, the load is defined. If you want to change them, you just right click and go to edit definition and change them, right? Or delete them. You can right click and delete them if you want to. So in order to create mesh, you right click on the mesh and then you say create mesh. And then you can have the density of the mesh, okay, whether you want smaller elements or bigger elements. As I said, the smaller the elements, the closer the approximation of the object to the actual geometry, and the more accurate the results, but of course more time. And I can show you here. Let's say I do a coarse mesh. Let's see what happens if I do that. So you see now the number of elements I'm using is not a lot, and I have some big tetrahedrons. And now, of course, if you look, the shape of the cross section, which is a perfect circle, is not the same as what I can get with all of these straight edges, right? The cross section right now is a polygon with here in this case I have what, 4, 9 times I guess each one of them is like 2 sides, so it's like 18 edges. It's a polygon with 18 edges instead of a real circle. Of course, I can never exactly get circle because tetrahedrons always have straight edges, but if I use a bunch of them, I can get much closer to the actual geometry. So it's still not horrible, but I can right-click on this, go to Create Mesh, and this time I do it with a finer mesh, and you can see the difference. So look. Now I'm using more elements, and now, of course, this is closer to a circle. But I have to wait a little longer for the result to kick in. But I guess that's good enough, and then I can, now that everything is good, I can say run this study. And as I said, it takes some time. And here we go. The first plot is in, and this plot is, if you see here, it's called one Mises stress. Now, what is one Mises? I'll mention later, but this is the stress plot. And if you look, there are some parts, some sections of the part which have a little higher stress. There are some that have lower stress. They are marked in blue. The high stress points are red. But the majority of the part that you can see is green, and green, the average stress here, if you look at the number, by the way, the numbers here are in Pascal, not in PSI. So one of the things you have to do is to change the unit of this to PSI so that we can compare it against this number of 12,700. Although if you want, I have written for you the Pascal version, but the Pascal version is, if you can see here, is like 87 megapascal. Okay, so 87 million or megapascal. And if you look here, the average of the green band is somewhere like 8.2 10 to the 7. So it's like 82 million or megapascal, while here is like 87. So it's not too bad, not too off. But let me also show you, as I said, there are some red areas which you can see at the fixture. So some areas in the fixture have higher and lower stress, but as you get away from the fixture and away from right under the application of the load, you can see quite uniform distribution of stress with an average of, like, as I said, close to 82 megapascal. Now, can I change the unit of that to PSI? Sure, but before that, was my design safe? Is this part gonna fail? How do I know? First is, you can see this is the yield strength for the part. How much is it? If you see, the yield strength for that aluminum is 2.7 10 to the 7, so it's 27 megapascal, while my stress is how much? 82. So my average stress way past the yield strength. So this part is gonna fail. This part is gonna fail, or at least for sure would deform permanently. So that's not a good design, right? But as I said, I can change stuff. I can show you even how the part would elongate and so on. So let me get you access to some of the stuff that you might be interested. So first thing, if you right click here under results, you see there are 3 different types of quantities that you can look. There is a strain. If you double click on the strain, you can see the strain, the amount of displacement per initial length, and then the pure displacement itself. And if you want this displacement, you can right click on it and you can say animate for me. And it can show you how the part is elongated. If it's too fast, you can make it slower. You can pause it. You can even save this animation to what? An AVI file movie and use it in your presentations. Okay, so you can do all sorts of things that you want to the animation. That's one thing. Now, for a stress, as I said, these are the numbers. I can right click on them. If you see, I have ISO clipping and so on that I can go and talk to you about it, but for the moment, if I click on the setting or chart option or edit definition, let's go to the setting first. So what do I have for the setting? So one of it is definitions. You see the type of a stress that is calculated is called von Mises stress. Is that the only type of a stress? No, there are other types of stress too, like normal stress in the X, Y, Z direction, and so on and so forth. Principal stress, shear stress. You might say, what are these? Well, you have to know again solid mechanics, otherwise it's quite hard for me to tell you. But the thing that I mentioned in this lecture was normal stress, and the force that is applied, if you can see, it is in the Z direction, so I can say normal stress in the Z direction. And the unit for it, instead of Pascal, I can change it to what? PSI, and now, you see, that's normal stress in the Z direction in PSI, and now you see the number is about 16,700, right? So 16,000, or actually it's the blue area. So let's see. That's the max stress. The average stress, if you look at the part with that shade of blue, is about 12,400. Okay, so it's 12,400, and the number I have is 12,700. So it's not too bad. It's not too off. But again, we have to know whether the part fails or not, and I guess I mentioned that to you, that you compare it, especially the highest stress parts, or at least the average part, versus the yield stress. So this is regarding displacement, stress, and strain, the basic kind of things that you have seen. And again, if I double click on the displacement, you see, for example, that the max displacement that I can have in the part in millimeter, it is this number, but again, I want it in inches, so I can right click here and go to the settings. And here, again, under definition, it says, what is it that you want? Resultant displacement, which is all of X, Y, Z together. I say, no, I just want Z displacement, and I want it in inches. Okay, and now if you can see, the max stress that I have here in the blue area is 2 to the 5, 10 to the negative 2. Okay, so 2.5, 10 to the negative 2, and if you look at this number here, this number is also 2.5, 10 to the negative 2. So you see, my max displacement is actually very comparable to the max displacement here. And my stress was quite close to here. Now, how can I get these numbers here to get closer to theory? By using a finer mesh. So I need to go back, I need to go under create mesh, I need to make this finer, and I need to rerun the whole thing. So now I make it finer, rerun it. Clearly this is a much finer mesh now. And again, I can say run this steady and look at the results again. I have to wait a little longer because this time I have a ton more meshes. And here it shows how much memory it is using out of your RAM. So if you're using a ton of mesh, make sure that your memory is good enough. And this is the stress this time again. And again, you can see that now my number here is about somewhere around 12,000, probably 300-400. which is similar to the number I got last time, a little bigger, which is closer to the theory. And then displacement and everything else. Okay, so by the way, the deformation scale here is much bigger than reality. I mean, when you right click and say animate this for me, the part is not going to elongate that much. I am right now animating this with a magnifier, basically, right? I'm magnifying it so that it is visible to the naked eye, because you know this number here is not a huge number. 2/100 of an inch over some time that you apply your force from 0, raise it to 10,000, it's not going to be super visible and big like that. That's because when I right click here and go to settings, okay, and go to definition, so here I can say the deformed shape is scaled up automatically to make it visible to your eyes, and here you can see the scale factor is 78. So what you saw in that animation was 78 times bigger than reality. I can say just do it true scale. So do not magnify it. Now let's see what happens if I do that. Look. Okay, you can barely see the displacement because it's a small number, but that is 1-to-1 scale. It's not magnified. Okay, so this is another thing that you have to keep in mind. Now, what else do we need to know? So I guess I mentioned these guys for you. Now, what is that 1 Mises stress? What is the principal stress? Here I mentioned the formula for them. This is for the case that you have more than one component of a stress. Stress in general is not like a single number. The stress can have different directions and different components. Actually, it is what we call a tensor rank 2. So it has 2 directions, and a stress can have up to 6 components: sigma x, sigma y, sigma z, and then tau xy, tau xz, and tau yz. So in general, I can have 3 different normal stresses and 3 different shear stresses in different directions and on different planes. And the question is, if I have to combine all of those 6 components into one single number that I can use here as the sigma to compare against the strength of the material, which one of those do I use? Do I use sigma x in that formula? Do I use sigma y? Do I use maximum of sigma xy and tau xy and so on? No, you combine all of them into a single number by different methods offered by different criteria or different people. One of them is the method that is suggested by the scientist von Mises, which is based on the distortion energy, and this is a method that you use if it's good for design and failure detection in parts that are flexible, or we call them ductile. So if the material is ductile, deformable, flexible, then we use the von Mises to combine all of the stress numbers into one single number. And if the material is brittle, on the other hand, then we combine the numbers using the principal stress method, and we use the maximum sigma, which is called sigma 1, and put it here. So the detail of that is beyond the level of this class. Again, you need to know solid mechanics or machine design to understand it, but just for your reference, I put them over here for you. So I mentioned mesh type, mesh control, everything, and what else do you need to know? So I said all of that, I assume, and use a smaller mesh to get more accurate results, especially when the boundaries are curved and not straight, because you're approximating the curved boundary by straight edges of the tetrahedron. But you can apply mesh control, and I mentioned applying external load, boundary condition, or fixtures. So I mentioned all of that, and then seeing von Mises strain, displacement. The other one is safety factor. I'm going to show you that. Just want to make sure that You know it. There are some details like Saint Venant theorem and so on that, again, it is good for you if you know the material, and I don't want to push you too much. So what I would do is, let me first show you the safety factor, and then we'll move on, because this topic is like a mini course for itself, simulations, and that's beyond EGR 295. So here I have shown you stress, displacement, strain. I showed you how to animate them, change the units, definitions, and so on. Now, if you right click here under results, okay, you can have fatigue and so on, but I don't want it. What I need is this one. It says define factor of safety plot, and you just can go into details of that and say based on what method you're looking at the safety factor. I say based on max 1 mices, or you can let SolidWorks decide for you how to calculate the max stress, and then divide the strength of the part by the max stress to get safety factor. So you can let SolidWorks check that for you, and if you get, then you have this safety factor plot. And if you look at these numbers, look at them, they are all 10 to the negative of 1. In other words, all of your safety factors are less than 1. Whenever safety factor is less than 1, it means the part is going to fail. Okay, so if you want a safe design, nowhere in your part you should have a safety factor less than 1. Everywhere it should be bigger than 1, never less than 1. If you see that, that means you have to redesign. Okay, so again here you can see that if I use my max sigma to be equal to the yield strength divided by safety factor, again the safety factor is always bigger than 1, but how can I calculate it for any point? At any point I divide the yield strength by the maximum stress at that point. And now how do I calculate this maximum stress? Based on which criterion? Is it 1 mices? Is it principal? Is it a simple normal stress? So that's what the SolidWorks asks you, which one, or do you want me to automatically do it? But you have to make sure this is bigger than 1. Anytime it's less than 1, between 0 and 1, that means failure. Okay, so bigger than 1 means it's not going to fail. Now, whether that's good enough, it depends on the application, but definitely less than 1 means danger. And you can see clearly all of the points here, even the best points, the points that are the closest to the 1 are still less than 1, because this is like 0.2, the safest point. So what I need to do in this case, I need to either make this part bigger, or I need to bring down the load, right? So if I say, well, maybe the load was not as big as this, maybe the load was, instead of 10,000 pounds, I made some mistake, maybe it was 1,000 pounds or 2,000 pounds or something like that. Okay, it wasn't really that big. Of course, typically the load is known, you have to modify the geometry or use a stronger material, because in a design you have 2 options, either choose the material or choose geometry or both, and recalculate everything. Then you can look at your safety factor one more time. Hopefully this time the numbers are more than 1. But here, just to make life easy, I just brought down the load for you by 5 times. Let's see what happens. Okay, so now if I go here and look at the safety factor, now you see that I have anywhere from 1.17 all the way to 3.6, and e to the 0 is 1. So you see nowhere I have among these numbers any number less than 1, so now my design is safe. But again, is that good enough? Is a safety factor of 3 or 1 good for this application? Well, it depends on where I'm using this shaft. Sometimes it could be good, sometimes it could be dangerous. So hopefully you got the very, very basic idea of design. Now, what else do I need to talk about? You can do more than that. You can even look at the reaction of fixtures. That's what probably you have done or you will do in your statics course, right? That I have a structure and I apply some force on it, and then it says find the reaction at the pivot or at the roller or at the fixture. You can even do that in SolidWorks if you want, right? So I can do that. And let me show you this. So if I go here in this example, remember that on this end I have a fixture, right? And when I apply that force here, there will be reactions at that fixture. How much are they? Well, let's see if we can find it. So I'm going to turn this off for now so that they are not shown. So I right click and say hide, and I right click on the stress, and it is already hidden, so I'm back to the geometry. Now I right click on the results and try to see the list. It says list result force. And here is your chance to select the edge or the face on which you want the reactions, and I say here, give me that and update for me, and there we go. Look, it says that there is no force in the x direction or none in the y, but in the z direction you have 8.9 e to the 3 Newton, and 8.9 e to the 3 is what? 8,900 Newton, which is equivalent to what? 2,000 pound forces. If you want, you can change this from SI to English so that you can clearly see that the Z force, of course, because your force P was applied in the Z direction, right? You can clearly see it in this figure that it was in the Z direction. So, of course, the reaction on that surface should be equal and opposite to P. And you clearly can see that, yes, it was 2,000, right? So you can clearly see the reaction over there. So this can be a good help to your statics class too. Okay, then we have probe, we have generating a report, and finally, maybe very fast, some frequency analysis, although frequency is quite beyond the scope of this class, but at least let me talk about generating a report and a probe option. So the probe is a nice thing. So here, if I show you the stress values, right, I say show it. So here is showing a legend, and then you have to guess, maybe at this point, this color is matching one of these, so you can approximately say how much the value of the stress is at that point or this point or this point. This is just a rough comparison against a legend, but can I exactly go to that point and exactly find the number? Yes. The way to do it is called a probe, and that's what you can see here. You can probe the value of any quantity at any location, and I'll show you that here. So if I right click on this stress, and then here you can see this item says probe. I click on this, and then it says, okay, what do you want? Do you want to do it at the location, at the node number, or selected entity, and so on and so forth? Do you know where you want to click? Okay, and it's not just as easy as I typically do not know the number of the node, but if I just click on the point, I can find it. So it says that point there is node number 58,000. The location of that is this, and the value of it is what? 2500 psi. So if you don't know the node number or the node location, don't choose these. Just directly click at the point that you want and say at location, right? And you can have several of these markers and you can see the exact number at those. So I recommend you do that one. And you can even see the average of all of these numbers that you clicked. So you can click on several points, and here it gives you a summary of those, right? What is the mean of those points? What is the max? What is the root mean square error? What is the average? And so on and so forth. So this probe tool is actually a very nice tool for exact value determination. And as I said, the final thing is generating a report, which is really good in SolidWorks, much better than CATIA. So if you go under the simulation tab, one option says report, and you can include a capture for it. You can add image, you can get the current view, and then you click on report. And the best thing about SolidWorks report is you can add anything you want to it and make it like a formal technical report. You can put your name on it as the designer, as the company, anything you want. Provide a path to it. Let me just add it maybe to the desktop. Give it a name and paper size and everything that you want. And it gives you something, as I said, like a technical report. And the format of that is Word document, so you can go in it and edit that. That's the best thing. If you have ever done that in CATIA, you see it's horrible. It's an HTML document. You can do nothing with it. It is very superficial, and I would never use the HTML document in CATIA for any report I want to give to my instructor. But I'll show you right now, this report of SolidWorks is actually quite amazing. So let it finish up and I'll show you. As I said, I can give you a very fast frequency or vibration analysis. And there we go. Look. The date, my name, everything, analysis type, table of content. Amazing, right? The information about the model, the mass of it, the volume, density, everything is given. A brief summary about the details of finite element method, the temperature, if it's there, sometimes you have temperature applied, the material properties, right? Yield, strength, tensile, Young modulus, Poisson's ratio. Some of these numbers you don't know right now. That's okay. You'll find out. And then the fixed geometry that you used, the amount of force that you used, everything, right? How many mesh points you have, the mesh size, right? Look, the size of the mesh is 0.12. How many total elements did you use? How many total tetrahedrons? 43,000. This is the shape of it. And then the reaction at the supports that you can see. And then this is the stress plot, of course. And then you have other plots too that you have done, right? This the safety factor, displacement, and so on and so forth. So this is really good. It leaves you a place to write your conclusion, discussion, and so on. So I absolutely love the type of reports that SolidWorks creates for you. So frequency analysis, I'm going to go very fast through this because it needs vibrations, which is a 400 level course that some of you might take. So I don't want to get into too much detail of that, just get you very brief intro to it. So here you can look at the vibrations of a part, free vibrations, which means no external force or anything. You just want to find free vibrations and natural frequencies of a part, which for designs they are important. And here this is an I-beam And this I-beam, I am going to look at how it can vibrate in different modes with their frequency. And again, I'm not going to go into the detail of calculation of the first natural frequency and whether the number in SolidWorks is close to the actual formula from the theory and what are these numbers. So just mention them here for you. If you later want to come back and look at this for your own knowledge, just very fast show you that. So this is the I-beam, and it is again from aluminum with some geometry, and I can click on new study, but this time I say frequency and I OK that, and all you need in this case is to provide the fixture where you want the part to be supported. And here I just do a cantilever on this end and no load because this is free vibrations, and then just make sure that the mesh is fine enough. There is a lot more to meshing. There are mesh parameters that you can choose, the size of the mesh that you can change, and whether you want curvature based mesh, standard mesh. Okay, there is advanced points for Jacobian and so many things that I do not want to get into. So let's see what happened here. So it says is not current, may have been updated, was modified. Okay, let me see if I can create something for this. That, there we go. So this is a simple mesh, and since the edges of the part are all straight, that's good enough. That's actually accurate. And now I can run this study and look at the different modes of vibration of this part and the natural frequencies. So here, this is what you can see. Under the results, as you can see, these are 5 modes of vibrations. Each one is different than the other in a different direction. So this one is, let me animate it for you. So this is a lateral deflection or bending. And you can see the numbers for it. Let me show you the numbers. So this is the number here. As you can see, the frequency of vibration for it is 142 Hertz. Then we have mode shape number 2, which is deflection in another direction. And the frequency for this mode shape is a little higher as you go more and more higher in mode shapes. What is mode shape? Again, you need to know vibrations. Sorry, but as you go more and more into the modes of vibrations, the frequency is getting higher and higher. So that is another deflection mode. This is the interesting one I wanted to show you. This is the twisting vibration, and the frequency of that is even higher, 389, and then you go into higher modes of deflection. Okay, so these are 2 other higher modes of deflection. And you might say, okay, what's the use of that? I know we don't have vibrations. Fine, you said it 1,000 times here. But what's the use of this? For statics, I know it's about whether the part fails or not. What's the importance of this frequency? So let me show you very, very fast something that might make you interested. So Tacoma Narrows Bridge collapse. Look at this video that you can search. It's a very famous video, of course, after you get rid of the ads. This is a famous bridge that was called Tacoma Narrows Bridge. As you can see, look, the bridge is just twisting, oscillating like crazy. And this is a huge bridge, very sturdy. And all there is right now is a very, very small wind that is coming. The wind by no means is strong, but look what that small amplitude wing is wind is doing to the bridge. Look, you might say, well, that could be a 400, 500 mile wind. That's not. It was like just only like 5 or 10 mile wind. So what makes this bridge oscillate and twist like this and then break? Look at that. Right? It's quite weird. That's something called resonance. And resonance is where there is an external force applied to your structure, and that force is changing its magnitude. Okay, the magnitude of it is not constant. It is going up and down. It has some vibrations in it. Okay, like when you play musical instruments, you are creating what? Sound waves, which are basically compressions and tensions of columns of air. That's the same thing with the wind. Not always the velocity of the wind is constant. It is kind of oscillating. And if the frequency of those oscillations is the same as what we call natural frequencies of your structure, that will create a huge displacement in your structure. Although statically your structure is fine, the stress should be way below the yield stress, and the structure should not fail or move crazy like this, but it does just because of that topic called resonance. And resonance will keep increasing its magnitude, and look, there we go. Look at here. That huge of a bridge with a 10 mile an hour or 5 mile an hour wind collapsed like that because the designers did not reinforce it laterally and they did not consider this resonance. Okay, so this is the most famous video you probably can find on YouTube about resonance and vibrations, and why vibrations and considering them is such a huge, important topic. So the bridge was exactly doing this. Okay, the frequency of the wind was the same as this frequency, for example, 389 for the bridge. And that's what makes this bridge do this crazy displacement.